Introduction then. I'm Angharad. I'm the curator at Creswell Crags. So Creswell Crags is a prehistoric gorge on the Nottinghamshire Derbyshire border in the UK, and we have lots of caves and rock shelters, and we've had lots of finds of paleontology and archaeology, mostly dating to the Ice Age from the site. So today I'm going to be talking about the Ice Age animals of Britain. So, oops, there we are. So firstly, I thought I'd talk about what the Ice Age actually is. So when you're thinking about the Ice Age, you might be thinking about a period that's cold all the time, where the land is covered by glaciers and ice sheets, and it's very snowy and quite barren. In actual fact, the Ice Age was not like this all the time. So this rather daunting graph is a sort of proxy for temperature. So this is the past 2.6 million years. So the Ice Age in this context is another name for what we call the Pleistocene. So the Pleistocene began 2.6 million years ago and ended 11.7 thousand years ago. So right on this sort of almost 0 point on the graph on the right-hand side. So the lowest points of the graph, the troughs of the graph, those are the glacial periods. So those are the cold periods that you might think about when you think about the Ice Age. But the peaks on the graph, those are the warm periods, the interglacials. So you can see that rather than the Pleistocene or the Ice Age being cold all the time, we had these massive fluctuations in temperature. And then I've just zoomed in to the past 300,000 years, just so you can see a little bit closer some of these climatic changes. And you can see that as well as the sort of the switches between the glacials and the interglacials, there were these shorter term fluctuations in temperature as well. And those are termed stadials and interstadials. And then I just want to point out around about the 0 point on the graph, that's today, that's the present day, and that's called the Holocene. So that's the warm period that we're in today, the interglacial that we're in today. So here are a couple of artist reconstructions of what Creswell Crags might have looked like at 2 points in the Pleistocene. And on the bottom right-hand side, we've got the late glacial period. So this is maybe more typical of what you might think the Ice Age might look like. So quite cool, quite cold, quite snowy, not very many trees around. But then on the left-hand side, we've got an image from the last interglacial period, 125,000 years ago. So I'll be talking a bit more later about the temperatures of this period, but it's quite, you can see from the image that it's warmer than the one on the right-hand side. And we've got a lot more trees around and also a lot more animal life hanging around the gorge as well. So speaking of animals, what sort of animals did we have in the Ice Age? So when you think of Ice Age animals, you might in particular think of the Ice Age large mammals, specifically the woolly mammoth and the woolly rhinoceros and the reindeer, and also perhaps the cave lion and the wild horse that are shown in this graph. And indeed, we did have animals like that at Creswell Crags and elsewhere in Britain. So on the left-hand side here, we've got an image of a baby woolly mammoth tooth. And on the right-hand side, we've got an image of a reindeer jaw, both found in Creswell Crags and held in the collections on site. But as well as these animals, as well as these big mammals, we also had smaller mammals, and we had other vertebrates such as birds and fish and amphibians. But there were, of course, other animals as well. So there were things like beetles, things like chironomids, which are non-biting midges. And you can see on the left-hand side here some images of chironomids head capsules, which preserve really well and which you can use to identify different chironomid species. And that's looking at them down through a microscope. We also had stuff like ostracods and mollusks and caddisflies. So in this talk, I am going to be sort of focusing mostly on mammals because that's what I know about most. But I am going to be talking about some of the other animals as well, because all of them are important in providing us a clear overall picture of the Ice Age. So the deposits then, so where are these animals found? So if we think about the animals such as the beetles, we tend to find them in deposits such as lake sediments and bog sediments, because these anoxic environments are really good at preserving remains of stuff like beetles and chironomids. So scientists will go to a lake or a bog and they'll take sediment cores and extract them, and they'll end up with sort of cores of sediments like shown in the image here. They can section the cores and process them, and then analyze the species of different animals found. But then if we think about the mammals then, so where do we find mammals? So we sometimes find mammals in open air deposits, such as found by the side of old river channels. So for example, on the left-hand side here, we've got an image or a drawing of a section through what's known as Barrington, which is in Cambridge. And you can see that the layer B is grey gravelly silt with bones and shells. So we've got the animals found there. And then on the right-hand side, we've got the Thames Terrace sequences. So a lot of animals have been found at different points along where the Thames River used to flow, such as Swanscombe and Grays and Trafalgar Square. And of course, most important for Creswell Crags are caves and rock shelters. So as I mentioned, Creswell Crags has over 20 caves and rock shelters, and these can be really important sites for finding the remains of Ice Age animals. So just as an example, I've got a drawing on the left-hand side, which is from Reverend Meggins Mellow's paper published in 1876 of excavations in Robin Hood Cave. And then on the right-hand side there, we've got an image from Paul Pettit's excavations just outside of Church Hole, which were undertaken in the early 21st century. And you can see a really nice reindeer jaw there. So how do animals end up in caves? So there are a number of reasons. A number of ways. So one of the ways is what's called a pitfall trap. So there might be a cave and there's an opening in the surface, and an animal might walk along, fall down into the cave, and then a carnivore might come along and be like, "Oh, what a tasty treat down there," similarly fall into the cave, and both animals are now trapped. Over time, a number more animals might end up inside of the cave, and their bones will be preserved and built up over time and buried by various sediments. And an example of a pitfall trap in Britain is Joint Mintner Cave in Devon. And then animals might end up in caves because they use caves. So for example, bears used to den in caves, and we sometimes find the remains of bears that might have died in the cave during hibernation. And another important species is the hyena. So the hyenas lived over most of Europe during the Pleistocene, except for really Scandinavia. And they used caves as dens. And in many caves, paleontologists have found remains of hyenas, sometimes numbering in the hundreds, if not thousands of specimens. And Creswell Crags is no exception. So in the caves of Creswell Crags, we've had people have found hyenas ranging from very old-aged adults through to juveniles, with prime-aged adults as well. So the full spectrum of ages. And one really special specimen that we have is a juvenile hyena, which is on display in our museum, and which we've got pictured here. So this juvenile hyena is almost complete. And I used to say up until a few weeks ago that almost complete Ice Age juvenile hyenas were quite a rare find in Britain. And that's for a number of reasons. So one of the reasons is that some of the bones are actually quite fragile, such as the bones of the cranium, so the skull and the mandible, and some of the tiny teeth are quite fragile. Another reason is through excavation bias, particularly by the early Victorian archaeologists and paleontologists who were more bothered about finding evidence of larger animals and also evidence of humans. So if they found some of the remains of a juvenile hyena, they might have kind of just discarded it. And another reason is hyenas' propensity to consume bone, which I'll talk a little bit about later. So despite all of these three reasons, this juvenile hyena survived for thousands of years and was excavated, and it was put back together a few years ago by a PhD student from Sheffield University called Jane Ford. So as I said, I used to say that Ice Age juvenile hyenas were quite a rare find in Britain. And that was until just a few weeks ago when a paper was published about a site called Cave Marie Jeanne in Belgium. And that paper stated that around 300 juvenile hyena skeletons had been found from that one cave. So not so rare anymore, especially not from that one site, but still a really special find for Curator crags. And as well as the remains of the hyenas themselves, the caves also yield the remains of their prey. So hyenas used to bring the remains of their prey into the caves, and the bones of their prey were also preserved alongside the hyenas. So I like to think if it wasn't for the hyenas, we'd actually know a lot less about the Ice Age, because we'd have a lot less mammalian remains preserved in these caves. And also small mammals were preserved as well. These include voles, such as the water vole, I believe, on the right-hand side, lemmings as well, and also pika, which is, I've got an image of on the left-hand side. So pikas are related to rabbits and hares, but rather than the big ears of the rabbits and the hares, they've got small little round ears. So small mammals might end up in cave deposits via a couple of ways. So one of them might be through the feces of small mammalian carnivores, and another way might be through birds of prey. So birds of prey would consume the small mammals, roost above a cave, and then regurgitate the remains of the small mammals out in their pellets. And if you're really lucky, some of these cave deposits might contain really, really rich remains of bones and teeth of small mammals. And some deposits, again, might contain hundreds of small mammal bones and teeth, really, really rich. And then finally, another way that mammal remains might end up in caves is through human activity, which I'm going to speak a bit about later. So what can animals tell us? So we found these animals. Obviously, finding the animals helps us to understand what animals lived in the area at different times in the Ice Age. But what else can they tell us? So mammals can be used for biostratigraphy. So biostratigraphy, by that I mean using either different groups of species or the presence of different individual species to tell us how old a deposit was. And mammals are particularly useful for this for a number of reasons. So one of the reasons is through their evolution. So we can see the evolution of specific species during the Pleistocene. Another reason is through migration. So their range will change in response to those climatic changes that I spoke about earlier. And another reason is through their extinction as well. And Britain is actually quite particularly useful for this because Britain at times was connected to mainland Europe and at times was separated. Sometimes in some species might have made it back to Britain when the climate changed, and some species might not have made it back to Britain. And that means that we have quite specific groups of animals at different times in the past. So I've just pictured the groups of animals found at 3 different points in the past here. And a lot of this work was done by Andrew Current, Roger Jacoby, and Danielle Shreve to understand what species lived at different times in the past. So I've got a period called marine oxygen isotope stage 11, and this was around about 400,000 years ago. So I won't go into what marine oxygen isotope stages are right now. I can tell you at the end if you're interested. But anyway, about 400,000 years ago, the mammal species that lived in Britain included 2 species of rhinoceros, wild horse, there was a straight-tusked elephant, Barbary macaque, and giant beaver. And then if we go forward to 125,000 years ago, we've got a different group of species. So we've got red deer, the straight-tusked elephant again, we've got the narrow-nosed rhinoceros again, we've got the hyena, and we've also got the hippopotamus as well. And then if we go to marine oxygen isotope stage 3, this is the middle of the last glacial. It was kind of cool, but not full glacial conditions. And this spanned from around about 55-ish to around about 25-ish, give or take a few thousand years ago. And again, we had the spotted hyena, we had the horse, but we also had reindeer and bison and aurochs and woolly mammoth. And I will just add that in the last interglacial marine oxygen isotope stage 5e, a notable absence from Britain was the horse and also humans. There appeared to have been no human species in Britain during that period. And the evolution of individual species can also be used to understand the age of deposits. And a really important species in Europe is the water vole. So the water vole has undergone considerable evolution during the Pleistocene. And one of these changes has been the evolution from the genus Mimimys to the genus Arvicola. And the Mimimys genus had rooted molars, and the Arvicola genus had unrooted molars. So I've just shown an image on the right-hand side, and these are 2 modern molars, just so you can see the difference between rooted and unrooted molars. So the tooth on the right-hand side is an unrooted modern water vole, and the tooth on the left-hand side is actually a bank vole, but just so you can see that it does have roots. So unrooted molars means that the tooth continuously grows. And this is advantageous for the water vole because its life isn't limited by the tooth wearing away so much that it is unable to eat. So because the tooth continuously grows, it doesn't reach a point where it wears so much that it can't eat. So this change from Mimimys to Arvicola happens during the early middle Pleistocene. So if you find Mimimys molars in a deposit, you know that the deposit was no younger than a certain time. And if you find Arvicola molars, you know that the deposit was no older than a particular time, a particular age. And then there was further evolution in the Arvicola as well. So there was a change from Arvicola terrestris kantiana to Arvicola terrestris terrestris, which some people now call the Arvicola amphibius. And there were morphological changes in the first lower molar of these Arvicola species. So on the right-hand side, I've shown the first lower molar here. So this is the first molar towards the front of the mandible. And some of these changes included a lengthening of the first lower molar over time, a change in the proportion of different areas of the molar, and a change in the area where the thickest enamel occurs. And if these different proportions and different measurements are measured in the Arvicola from a sample, you can compare those to molars from other samples of known ages, and that can help you to determine an age for your sample. Mammals can also be used for radiometric dating, and in particular radiocarbon dating. So they can, in some cases, provide more specific dates than biostratigraphy, although biostratigraphy is still a very important method. And radiocarbon dating is limited. So, for example, it's limited to animals that lived no older than around about 50,000 years ago because of the sensitivity of the method. And also you kind of have got to be aware of how the bones and teeth of the animals were treated in the past. For example, earlier archaeologists and paleontologists might have treated the bones and teeth with animal glue or varnish. And this might contaminate the bone or tooth. So the more modern animal glue or varnish contains more modern carbon, and that might provide an erroneously young age estimate for the bone or tooth. However, given strict protocols and given more modern methods of filtering out contaminants, radiocarbon dating can be a really important method. So that can go from helping you to understand the age of an individual to putting a load of radiocarbon dates in a model, such as this slightly intimidating figure on the right-hand side. And that can be used for determining the ages of a deposit, or also for determining the presence of an individual species, and to help you understand the timing of its extinction from an area. And then animals can help us to understand past environments as well. So, for example, we might have an animal that might tell us that the area was forested at the time, or maybe it preferred local grassland. So understanding where the animal lives today and the environment that it inhabits today, we can infer what the environment was like in the past. Although we do need to bear in mind that humans have sort of restricted a lot of species to their environmental ranges today. We can also understand temperatures as well. So if we find, for example, a lemming or a steppe pika in a deposit, that helps us to understand that it was cold at the time that those species were living in that area. Also, some species can help us to understand a quantifiable temperature as well. So two really good animals for this are beetles and ostracods. So there's the mutual climatic range method using beetles and the mutual ostracod temperature range method using ostracods. So what scientists will do, they'll sort of take a sample of sediment. They'll identify the species of beetles and ostracods from that sediment, and then they'll look at where those beetles and ostracods live today. And they'll look at what those temperatures are like in the areas that they live today. They'll take all of those temperatures, put it into a model, and that'll give the scientists an estimate of the winter and summer temperatures of that deposit, of that area, of that time in the past. And I just want to briefly outline a case study of the last interglacial, so 125,000 years ago. So Ian Candy and others in 2016 published a paper reassessing the temperature reconstructions from various sites that date to the last interglacial. And there are a variety of methods used to reconstruct the temperatures. Some of them included the beetle and the ostracod models that I've already discussed. And some of them included the presence of thermophilous species, so warm-loving species. So the methods found that from Trafalgar Square, the summer temperatures were around about 20 to 21 degrees Celsius, and the winter temperatures were around about 1.5 to 3 degrees Celsius. However, the researchers found that temperatures from other sites were actually lower. So from these other sites, the average summer temperatures were slightly warmer than today, and the average winter temperatures were slightly cooler than today, indicating increased seasonality. So the researchers stated that if the temperatures from Trafalgar Square were true, then this period of enhanced warmth, warmer than reconstructed in other areas, might have only occurred for quite a short amount of time during the last interglacial. And by a short period of time, the estimated may be less than 1,200 years, which given the vast period of the Pleistocene is actually quite a small period of time. And then finally, as well as temperature and vegetation, animals can help us to understand precipitation. So if we think about the woolly rhinoceros, we might think that because of its thick fur, it would have been able to tolerate quite a lot of snow. But actually, if we look at its morphology, it had quite short, stubby legs. So if we think about if there's quite a lot of deep snow and it's got short, stubby legs, it might not have been able to traverse landscapes with a lot of deep snow. So if snow was present at the time that a woolly rhinoceros lived in an area, it wouldn't have been deep for very long. It would have had to have been quite shallow snow for it to have been able to survive. And we can also understand the behavior of animals as well. So we can look at the animals to understand their migration. So I've got an example of a really nice study here. And I'm actually going to sort of move out of Britain just briefly to an area called Jonzac in France. And this was a study undertaken by Cape Breton and others. And they looked at the migration of reindeer and also bison. And the way that they did that was looking at strontium isotopes. So they sampled the strontium isotopes from the reindeer and bison teeth. So the strontium isotopes found in the teeth are a reflection of the water that the animals were drinking in an area. And the strontium isotopes of the water are a reflection of the strontium in the local geology. So the strontium is incorporated in the teeth when the teeth are actually growing. So the scientists found that the strontium isotopes of the reindeer teeth did vary and also were not reflective of the strontium found in the Jonzac region. So they interpreted this as meaning that the reindeer were migrating over vast distances, and the time that they spent in Jonzac was actually quite a short amount of time. By contrast, the strontium found in the bison teeth was reflective of the Jonzac region. So at least for this particular time, the bison were not migrating very far at all. And we can also understand past diets of species as well. So one of the methods of this is looking at the damage to bones and teeth. So if we want to understand diets of humans, we can look at damage such as cut marks and breakage marks as well on the bones and teeth. So at Creswell Crags, we have evidence of human diet from the late glacial, so Homo sapiens diet. And we understand that humans were consuming mountain hare and wild horse. And elsewhere in Britain, in King Arthur's Cave, there was damage to wild horse and red deer, indicating that humans around King Arthur's Cave were consuming those two species. We can also look at the damage to bones from other species as well. So as I mentioned earlier, hyenas have a propensity to consume bone, and they're really well suited to doing this. So they have these big conical premolars, such as this third premolar here. And that's a really good shape for being able to crack bone. They've got deep mandibles, which are able to withstand the stresses placed upon them by cracking bone. And they have really big and powerful jaw closing muscles as well. So hyenas will consume bone, they'll gnaw bone, and a lot of the bones found in hyena dens exhibit quite distinctive evidence of hyena gnawing. So one example is this bone on the right-hand side here. So the edges of the bone are quite crenulated and rounded, and this is indicative of hyena gnawing. And from the bones found in hyena dens, we understand that they were consuming quite a wide range of species, similar to the spotted hyenas that live in Africa today. So hyenas in Britain were consuming species such as wild horse, woolly rhinoceros, woolly mammoth, particularly the juveniles, various deer species, aurochs and bison. And as well as the remains of their prey themselves, we find the remains of their coprolites, so fossilized poo. So hyenas, as well as being well adapted to actually cracking the bone, their digestive systems are really good at digesting bone as well. So they digest all but the inorganic portion of bone, and the calcium carbonate content comes out the other end, makes their poo white, and helps their poo to preserve for tens of thousands of years. And there was a study by Bon et al. Who looked at the DNA found in hyena coprolites, and they found red deer DNA. So presumably the hyena that deposited that specific coprolite had consumed at some point some red deer. Palaeodiet can also be understood by looking at dental microwear. So that's the microscopic features on the surface of the tooth, which are incorporated on the surface of the tooth during eating. So one method of looking at dental microwear is through taking a mold of teeth using dental putty and dental silicone. And then this mold is filled with resin. And it's actually this resin replica that is analysed under a microscope using sort of oblique lighting. And Katerina Bassel is one scientist who has done a lot of work understanding dental microwear, and in particular, she was focused on carnivores. So she analysed the pits, the scratches, and the gouges on the surface of carnivore teeth. And she found that hard food consumers had a greater number of pits. And she classified hard food consumers as those consuming bone, as those consuming shells, and as those consuming fruit because of the seeds and the stones in the fruit. They would also impart damage to the teeth. She also found that spotted hyena in particular exhibited a greater number of pits, scratches, and gouges relative to species such as red fox and cheetah, which consume softer foods. So understanding the signatures of microwear exhibited by animals today can help us to understand the diets of carnivores in the past. We can also look at isotopes to understand past diets as well. And in this case, we're looking at carbon and nitrogen isotopes. So a number of studies have been undertaken in Britain by Rhiannon Stevens and also by Richards, looking at the diets of humans in the Pleistocene. So dietary isotopes of Homo sapiens from Gough's Cave and Sunhole indicated that they were consuming aurochs and red deer primarily, with the occasional consumption of horse. And isotopes from Kendrick's Cave indicated a mixed diet of terrestrial mammals, but also marine mammals as well. And as well as understanding the diet of individual species, isotopes can help us to understand competition. So again, I'm just going to briefly leave Britain to look at Germany. So there's a really nice study done understanding the past diets of hyenas and cave lions in Germany. So the isotopes indicated that hyenas were consuming a wide range of species in Germany during the Pleistocene, but at the same time, the cave lions were restricted to consuming reindeer and also bear cubs. This was apart from the point after which hyenas disappeared. So after hyenas disappeared from this area in Germany, the cave lions appeared to have been eating a wider range of species. So it seems like when hyenas and cave lions were coexisting, hyenas were outcompeting the cave lions for a lot of the different prey species. So they had the lion's share of the prey, as it were. And then we can also look at the morphology of the bones of species. So again, I'm going to be talking about hyenas for this example. So we can look at the bending strength of the mandible. So this is the ability of the mandible to withstand stresses placed upon it. So if we look at this area here of the mandible, below and directly behind the premolars, the deeper this area is, the better the ability the hyena had to withstand the stresses placed upon it by cracking bone, because particularly because these premolars are the teeth most used for cracking bone. And then we can also look at bite force, or a proxy for bite force, by modeling the mandible as a lever and using sort of mechanical engineering principles. But essentially, the greater the inferred bite force, the greater the ability to crack bone as well. And also we can look at tooth breakage as well. So teeth tend to break through sort of grappling, struggling prey, but also, again, cracking bone. So if we have a deposit that has a greater number of broken premolars, that indicates that that the hyenas in that area were consuming more bone. And this can help us to understand the stresses placed upon hyenas in the past. So hyenas, even though they are quite adept at consuming bone, if there's quite a lot of fresh food available, you kind of assume that they would sort of concentrate on the fresh food, the meaty parts, with maybe a bit of bone consumption. If there's not very much food available, if there's dietary stress because of either high competition or sort of few herbivores available, hyenas would have had to have consumed all of the carcass in order to survive. So greater bone consumption might indicate greater dietary stress at points in the past. And then we can look at the remains of animals found in caves and other deposits and determine the tools that were found, manufactured by humans, created by humans. So a wide variety of tools have been found from Britain, dating to the Upper Paleolithic. I've just got two examples here from Creswell Crags, and that includes a bone awl and a bone needle. And one of these, I think it's awl, was made from a mountain hare bone. And then art as well. So art has been, animals have been incorporated in Paleolithic art as well. So again, we've got two nice examples from Creswell Crags here. So we have cave art engravings in Creswell Crags, particularly church hole. And these were discovered by Paul Pettit, Paul Barn, and Sergio Ripoll in 2003. And one of my favourite examples of the rock art is the bison. So hopefully you can see my mouse pointer. So I'll just highlight the bison because it's a bit difficult to see. So we've got its face here, we've got its eye, we've got its down its muzzle, up, and that's its front leg. And that's sort of the shoulder area of its front leg. If we go back to its eye, we're going up, and they're going up its horn here, back down its horn, up the hump on its back, and then down its back. And that is a really, really lovely example of a bison engraved into a church hole. And other animal species engraved into church hole include a red deer and some ibis as well. And then on the right hand side here, I've got what's known as the ochre horse. So this is an image of a horse's head engraved onto a rib bone. Found in church hole, found in Robin Hood Cave in Creswell Crags, although there's a fair amount of controversy about this. So this was discovered by William Boyd Dawkins in the 1870s. It was found in the same week as he found a Homotherium tooth, so a scimitar-toothed cat tooth. And a Homotherium remains and evidence of Paleolithic art were quite rare finds in Britain at the time. And some people thought that he might have planted those items in Robin Hood Cave to further his career and potentially to feed his ego, as it were. That there's a transcript or a sort of documentation from a geological society meeting in Manchester. And on one hand, there's William Boyd Dawkins and Megan's Mello sort of asserting that these finds of the incised rib and the Homotherium tooth are genuine finds and genuinely were found in Robin Hood Cave. On the other hand, we've got people such as Thomas Heath, who'd had a falling out with Dawkins and Mello, and he's saying that it was planted and it's all a hoax. So this documentation essentially just shows an argument between these three excavators in a scientific geological meeting in Manchester. As well as art, there's evidence of ornamentation. So there's the Red Lady of Paviland burial, although I think it's actually proven that it was a man rather than a lady. But there's a lovely examples of perforated periwinkle shells. So humans perforated these shells, and these shells might have been strung together and they might have been potentially used as decoration or jewellery. And again, I'm just going to move out of Britain for a little bit to look at a cave in Poland, because it's a really nice example of a pendant. So in a paper published by Talamo and others in just last year, they found this example of a pendant from this cave in Poland. And they used a method called collagen fingerprinting, or zooms. So collagen fingerprinting is a method by analysing the collagen from teeth or ivory or antler, because different genus or species of animals have different sort of collagen, essentially fingerprints. You can identify the genus or the species based on the collagen. And they found that this was mammoth ivory, and they dated this pendant to around about 41,500 years ago. So it's an oval shape with rounded margins, and it has 2 drilled holes. And they determined that there's also punctures. So you can kind of see some punctures decorating the pendant. And they determined that these punctures are so similar in their outlines and cross sections that the punctures are likely made by the same tool. So that's another really nice example of ornamentation. And then I'm just going to finally finish off by talking about instruments. So as far as I'm aware, we don't really have any evidence of musical instruments found in Britain from the Pleistocene. So I'm just going to quickly give 2 examples. So we've got this example on the left-hand side from Slovenia, although this is slightly contested. So this is apparently a flute made from a cave bear femur, dated to around about 40,000 years ago, and potentially made by Neanderthals. But there is debate about whether the holes were made by Neanderthals or whether this bone just exhibits damage by hyenas. So some people argue that the particular spacing of the holes indicates that the bone was modified by Neanderthals. However, there does appear to be some rounding and crenulated of the edges, which might indeed be indicative of Neanderthal gnawing. However, there's also other examples made by Homo sapiens, such as this flute from this cave in Germany. I won't attempt to pronounce it because I know I'll mispronounce the name. So there are examples of flutes made from the bones of griffin vultures and ones of swans. And also there are flutes made from ivory as well. And I just want to read out a quote from a paper by Conrad and others in 2009, because it really does illustrate the genius of the technology for creating flutes from ivory. So they said, the technology for making an ivory flute is much more complicated than that for making a flute from a bird bone. It requires forming the rough shape along the long axis of a naturally curved piece of mammoth ivory, splitting it open at the interface of the cementum and dentine or along one of the other bedding planes in the ivory, then carefully hollowing out the halves, then carving the holes, and then rejoining the halves of the flute, and even making sure that the edges are airtight along the seams that connect the halves of the flute. So a massive amount of preparation undergone to create these flutes from mammoth ivory. It's just remarkable. So I thought I'd finish off with that beautiful example. So obviously this has just been a whistle-stop tour. There is so much more to understand about animals in Britain and indeed the rest of Europe and the rest of the world. I just thought I'd outline some of the important things that we can understand and just some really nice case studies as well. So Daryl just wanted me to include a bibliography at the end. So these are just some of the studies and papers that I read. There's obviously lots more out there, and some of these may be behind paywalls, but hopefully you can get hold of some if you want to. So thank you very much for listening. I'll stop sharing now and I'll answer any questions that you might have. So I've got a question. So why make casts of teeth for microanalysis when looking at it in oblique light is a non-destructive technique? So that's a really good question. So actually making casts of the teeth is a non-destructive technique as well. So all you need to do is really gently clean the surface of the tooth. And so long as the tooth isn't delicate, you can create the cast and remove the cast. So you can create the mold and remove the mold without damaging the tooth. It's the same material that dentists actually use to create molds of our own teeth. So our own teeth aren't damaged by the methods of the dentist. And I believe looking at it through this sort of semi-transparent resin replica just helps to highlight the microwear much more clearly than other methods do by looking at the tooth itself. I know a lot of people have undertaken a lot of work to determine the best lighting and the best methods, and that just seemed to be one of the really good methods. There's also methods by looking at it through a type of microscopic technique, SEM, but that's a lot more expensive, and you've got to have a lot more high-tech equipment for doing that. So cut marks on hair bones, were they all from skinning, removing the fur, or were they from removing the meat prior to cooking? I think they were from both. I think there's a paper published by Charles and Jacobi, I believe, who looked at the cut marks from the mountain hair bones at Creswell Crags. And I believe they showed that it was the cut marks were produced from basically all manner of processing techniques. I think they indicated that the humans were using as much as of the hair bone of the hairs as they could, so for the skins, so for the meat, and also as indicated from the artifacts for stuff like creating tools like awls as well.
I just want to thank you for a super presentation. Thank you very much. For giving us your time this evening, and particularly for adding the extra bits like the bibliography, the extra work that you've done for us today. Thank you very much.
Well, it was my pleasure. Thank you so much for inviting me to talk. I really enjoyed creating this presentation because it's what I love, particularly mammals and the hyenas, if you couldn't tell. And thank you for everyone for coming as well. It was a real pleasure. So hopefully we'll see some of you at a Creswell Crags events in the future then. Okay. So bye-bye, everybody.
Thank you.